Every dataset hides a process. An online store records clicks, orders, delivery times, and product choices. They may look like unrelated columns, but each column is the trace of something uncertain happening in the real world. Imagine that the store observes 100 visitors and 30 of them click. The raw data is a row of zeros and ones. We can compress that row into a relative frequency. 30 divided by 100 equals 0.3. That number estimates the probability of a click. If we repeat the day, the count will not always be exactly 30. It may be 27, 31, or 35. The variation is not merely noise to throw away. Its pattern tells us how the generating process behaves. A dataset is a shadow of that process. A probability distribution is the mathematical shape casting the shadow. It assigns a probability to every possible outcome. Once we learn that shape, we can describe what is typical, quantify uncertainty, and recognize what is surprising. To describe an uncertain process, we first name its output. A random variable is a rule that turns an outcome into a number. Let x equal 1 when an email is spam and 0 when it is not. X might instead count clicks per hour, measure height, or record a model's prediction error. Random variables come in two broad types. A discrete variable has countable outcomes, 0 orders, 1 order, 2 orders. A continuous variable can take any value in a range, such as a height of 174.3 centimeters. For a discrete variable, the probability mass function gives the probability of each exact value. P of x equals x. All of its masses must add to 1. In this example, 0, 1, 2, and 3 clicks have probabilities 0.35, 0.3, 0.22, and 0.13. Their sum is exactly 1. A continuous variable uses a density, f of x. Density is not probability at a point, it is probability per unit along the horizontal axis. The probability that x lies between a and b is the area under the curve, the integral of f of x from a to b. The total area is 1. For a roughly normal height model with mean 125 centimeters and standard deviation 5, the interval from 170 to 180 is 1 standard deviation around the mean. Its probability is about 68%. That shaded area, not the height of 1 point, is the probability. Start with 1 visitor. Let x equal 1 for a click and 0 for no click. If the click probability p is 0.3, then p of x equals 1 is 0.3, while p of x equals 0 is 1 minus p, or 0.7. This two-outcome model is the Bernoulli distribution. Now observe 10 independent visitors with the same click probability, add their 10 Bernoulli variables. The total x counts clicks and follows a binomial distribution with n equal to 10 and p equal to 0.3. What is the probability of exactly 3 clicks? There are 10. Choose 3 ways to choose which visitors clicked. Each such pattern contributes 0.3 cubed times 0.7 to the 7th. Multiply them, and the answer is about 0.267, roughly a 27% chance. The full formula is p of x equals k. N choose k, p to the k, times 1 minus p to then minus k. Its mean is np, and its variance is np times 1 minus p. So among 100 visitors, we expect 30 clicks with a standard deviation of about 4.6. Expected does not mean guaranteed. Seeing 30 is common. Seeing 50 would be far from the center and evidence that the click rate may have changed. This is why the binomial model is useful for conversion rates, A/B tests, and uncertainty around classifier accuracy. A product choice has more than 2 outcomes. Suppose a classifier produces raw scores, called logits, of 2, 1, and 0.1 for shoes, bags, and tech. Scores are not probabilities. They can be negative, and they do not have to sum to 1. Softmax exponentiates each score and divides by the sum of all exponentials. These 3 logits become approximately 0.66, 0.24, and 0.10. Every value is between 0 and 1, and together they sum to 1. That probability vector describes one multinomial, or, for one draw, categorical choice. Training a multi-class classifier rewards probability placed on the true class. If the true class is bags and the model assigns 0.24, its cross-entropy loss is negative log of 0.24, about 1.43. Raising the true class probability lowers the loss. Uniform uncertainty has a different shape. For x uniformly distributed between a and b, the density is constant, 1 divided by b minus a. On the interval 0 to 1, the density is 1, so the probability between 0.2 and 0.5 is simply the interval width, 0.3. Uniform sampling powers simulation, data shuffling, and controlled random initialization, but uniform does not mean random looking, it means equal probability for equal length intervals. Delivery time errors often cluster near zero. Small errors are common and large errors are rare. The normal distribution captures that bell-shaped pattern. Mu controls the center and sigma controls the spread. The variance is sigma squared. Its density is 1 over sigma times the square root of 2 pi multiplied by an exponential penalty for squared distance from mu. The formula looks dense, but its geometry is simple. Moving away from the center rapidly lowers the density. Standardization measures distance in units of spread. The z-score is x minus mu divided by sigma. If delivery error has mean 0 and standard deviation 5 minutes, an error of 10 minutes has z equal to 2. It is 2 standard deviations late regardless of the original units. The 68, 95, 99.7 rule makes this practical. About 68% of normal values lie within 1 sigma of the mean, 95% within 2, and 99.7% within 3. Linear regression often models residuals as independent normal errors with constant variance. That assumption gives us likelihoods, confidence intervals, and prediction intervals, but it should be checked. A bell curve is a model of the errors, not a law that every dataset must obey. Suppose the store receives an average of 3 orders per hour. The Poisson distribution models how many events occur in a fixed window when events arrive independently at a stable average rate lambda. Its probability mass function is e to the minus lambda times lambda to the k divided by k factorial. With lambda equal to 3, the probability of exactly 3 orders is e to the minus 3 times 3 cubed over 3 factorial, about 0.224. A special Poisson property is that both its mean and variance equal lambda. A much larger empirical variance signals burstiness or changing rates, warning us that a simple Poisson model may be inadequate. Now ask a different question, not how many orders arrive, but how long until the next one. Under the same Poisson process assumptions, waiting time is exponential. Its survival probability is p of t greater than t equals e to the minus lambda t. 3 orders per hour means an average wait of 1 over lambda, 1/3 of an hour or 20 minutes. The chance of waiting more than half an hour is e to the minus 1.5, about 22%. Count and waiting time views are 2 sides of the same process, useful for traffic forecasting, queuing, and predictive maintenance. These distributions are not labels attached after modeling, they determine what a model predicts and how it learns. Logistic regression outputs a Bernoulli probability, softmax outputs class probabilities, Poisson regression predicts counts. Linear regression often places a normal distribution around its predicted mean. The unifying idea is likelihood. Given parameters theta, how probable was the data we actually observed? Training usually maximizes the product of those probabilities, or equivalently, minimizes the negative sum of their logarithms. For classification, that negative log likelihood becomes cross entropy. If the true class receives probability 0.8, the loss is negative log 0.8, about 0.22. If it receives only 0.05, the loss jumps to about 3. Confident wrong predictions are penalized heavily. A learned distribution also gives an anomaly score. Values in high-density regions are unsurprising. Values in the tails have low likelihood and high negative log likelihood. But low probability is a flag for investigation, not automatic proof of fraud or failure. Generative models go further. They approximate the full data distribution so they can sample new images, text, or audio. Across all these methods, the distribution turns a point prediction into a statement about uncertainty. One online store, 7 useful shapes. Use Bernoulli for 1 click and Binomial for the number of clicks in repeated independent visits. Use multinomial probabilities for a product category and uniform when equal size intervals should be equally likely. Use a normal model for symmetric measurement or prediction error, a Poisson model for event counts in a fixed window, and an exponential model for time until the next event. The right choice begins with the question: binary outcome, category, count, measurement, or weight. Then test the assumptions. Are trials independent? Is the rate stable? Are errors roughly symmetric? A distribution is useful because it is a checkable mathematical model, not because its name sounds familiar. Machine learning is not only learning from isolated data points, it is learning a hidden distribution: what is common, what is rare, how uncertain a prediction is, and when the world may have changed. In the next chapter, we turn these distributions into numbers we can compare: expected value, variance, and covariance. Thank you for watching. Stay curious and keep exploring the shapes behind your data.